So let's take a more general system. So if you have a numerator by denominator polynomial, and then you can write it in this format. So we have z s plus z1 times s plus z2, so on and so forth, up to zm, divided by s plus p1 plus times s plus p2, so on, times to pn. So where z's would be the zeros and p's would be the poles. And then if you take the input in this format, s plus z sub u1 and so on and so forth, so what will be the system? The response of the system, if you recall, is going to be g times u, and so this is the product that we get. So essentially, we have the potential for terms in here canceling out terms in here, and so on and so forth. So now we're going to do some exercise to figure out, or at least kind of appreciate the importance of Laplace transformation. So what we're going to do is we are given this transfer function of the system over here, and then we're going to calculate the response to a step input, which is u equal to 1, as well as u, or the input, is 1 plus e to the minus t. Since the g is actually y over s, so what actually happens is y is g times u. So essentially all of this just becomes like multiplication in the Laplace domain. So this is s plus 1 divided by s squared plus 5s plus 6 times u of s. What we need to do is determine the Laplace of the input, and then if we can do that, we can substitute this value. So the Laplace of the input is 1 over s. How do I know that? Is from the Laplace table over here. So if we go all the way up, so we have u of t, which is just an input value, unit step. The Laplace is 1 over s, and so that's what we substitute over here. So you would have this table in back of Professor Goldenragi's book. So we're going to use that as a reference. So once you have that, so we're going to calculate the response of the system. So it basically becomes just g times 1 over s. So if we go back, we have two options over here, right? So we can multiply the denominator out, where I'll get cubic terms, and then try to figure out what the inverse Laplace is going to be. But then if you go to the Laplace table, it only has terms up to s squared. Right, so this would be a problem. So what we need to do is kind of go in the other way, is to actually figure out some way of transforming this equation into a combination of lower powers of s in the denominator. So before we do that, so what we need to do is calculate the roots of the system and then use that information just a bit. So what we do is first solve for the denominator over here. So it's s squared plus 5s plus 6. So we use the method of, so we solve, so this becomes minus 5 plus or minus square root of 5 squared minus 4 times 1 times 6 divided by 2 times 1. And then if we substitute, we get s is minus 2 and minus 3. So hence, the denominator can be written as s plus 2 times s plus 3, or we multiply this out. So the equation y of s should be s times s plus 2 times s plus 3, the denominator, and then s plus 1. Right? So this again doesn't solve because the Laplace transform doesn't really have multiplications either. So the next thing is we need to figure out how to convert this into a sum of Laplace, which we know how to solve. So this is where the method of partial fraction comes. So we are, for more details, you can look at the section 2.5 in Dr. Goldenragi's book. So the basic idea is, so we do the Laplace transform, and inverse Laplace transforms are additive. We have Laplace transform for simple terms like 1 over s, 1 over s plus a, and so on. Hence, we'll convert our complicated fraction into sum of simpler terms. The idea is we are going to find some constants k, so that our equation here is identically equal to, this three lines means identically equal to, which means it's true for every value of s. So it's going to be the sum of these three values. So the reason we get this is if we multiply all the three denominators, we end up with the denominator on the left hand side. So that's the only way. And so we have like additional terms. If I put k4 by s plus 4, because I wouldn't have anything in the denominator. So those terms would be 0. So this is how we do. So typically we factor the denominator, and then we actually have as many terms as the number of products over here. So once we have that, so we need to equate this. So we're going to multiply the terms and then equate the powers of s. So how do we do that? So we're going to rewrite the right hand side. So we multiply this. So this becomes k1 times s plus 2 times s plus 3, which is going to be these two. And then k2 times s plus 3. And then k3 times s plus 2. Essentially what happens is whatever is there at the denominator, that term would be missing from this product over here. Right? So once we do that, so we're going to compare the two terms. So we're going to select the term so that this term over here should be identically equal to the previous term over here. So how do we do that? So essentially we are going to just compare the coefficients of different terms. So here if we multiply this out, so we're going to get different powers here. So let's look at terms that will contain s squared. So you're going to have k1, and then this is going to be k2 and k3. So we're going to have powers of s squared is going to be k1 plus k2 plus k3. And then on the right hand side, since there is no s squared, this sum should be 0. We look at the power of s, so we multiply that out. So we get s times 3 plus 2, and then we multiply, we get 5 k1 plus 3 k2 plus 2 k3. And then for the constant term, we get all of the constants. So 2 times 3 is 6. And then we don't get any constant term from here. And then we don't get any constant term from here. So we have to solve these equations. So we have three unknowns, k1, k2, and k3. And then we have three equations, and we can solve it. So this is not particularly difficult. So what you can actually do is use the last equation over here to solve for k1, which is going to be 1 over 6. We can eliminate k1, and then we have two equations, and then we solve for k2 and k3. So you can pause and then calculate these values. And then once we do that, we can substitute the values. So we get k1 is 1 over 6, and then k2 is 0.5, and k3 is 0.6667. So these are rounded off. And so what do we do next is, because we know the inverse Laplace of s plus 2 and s plus 3, if we calculate the inverse Laplace of y, we get the sum of those terms. So we get y is 1 over 6 or 0.1667 plus 0.5 e to the minus 2t and minus this and so on. So again, how do we get this? Again, we look at the Laplace table. So the inverse of 1 over s is just a step. So the inverse of s plus alpha is e to the minus alpha t. And so we can just substitute those values over here. And so just to look at this, if you look at taking t to infinity over here, these two terms disappear, and then we get 0.1667. And just for the fun of it, you can put in other values. So essentially, we'll expect a short overshoot. So the other examples are like for you guys to try it out yourself and then see something interesting that happens, and then you're going to write a comment on the video or submit it as the like the response to the video. All right. Finally, what we're going to do is look at the effects of the poles. So we're going to imagine we have a system which we have written on the form k divided by s plus alpha times s plus alpha 2, alpha 3, and so on and so forth. So let's see what actually happens if all the poles are negative. So essentially, if all of the poles are negative, so what happens is, since the response is going to be y is beta times, so essentially you'll have some constant using our partial, the partial fraction analysis that we did. So we would actually have an equation of this form for the response of the system. So if all the poles are negative, so all of these terms are exponentially decaying. So just a quick caveat, so you could potentially change these locations of the pole with feedback, but for now, you're going to ignore the effect of the feedback and then see what actually happens. So now, if all the poles are actually negative, the system response eventually goes to 0. If any one of these is actually positive, the system response actually blows up. So essentially, you can say if all the poles are negative, the system is stable. If one of it is actually positive, then the system response goes to infinity or the system blows up. So the positiveness of the pole actually indicates system instability. So this basically concludes our quick introduction on the chapter and the quick introduction to or quick recap of the concepts in control system. And then in the next video, we'll start looking at more interesting stuff in the state space domain. Thank you for watching and have a great day.